All right, wonderful. All right, can everybody hear me well?
Yes.
Perfect. All righty. Well, today is our webinar, and we have a very special guest here. So I'm thrilled to be able to introduce Dr. Michael Coughlin, who will be presenting with us today. Many of you may be familiar with his name, but you might not know his role within Kilonova-Catcher. Michael is an assistant professor at the University of Minnesota, where he recently earned tenure, and he brings exceptional expertise to our field as one of the primary Sky Portal developers and a co-founder of Grandma. His research and my own focuses on developing machine learning tools to discover optical counterparts to gravitational waves and other electromagnetic transients. This is work that sits on the cutting edge of what we're all really trying to accomplish here at Kilonova-Catcher. Today, Michael will be presenting on Boom, an exciting new broker currently under development amongst a few other institutions and the University of Minnesota. Michael is my supervisor and mentor. I have been with him for many years, and he is a phenomenal individual to listen to and to present with. So, Michael, I give you the floor.
It's one of the benefits of paying Christina. She has to say nice things um, whenever I present. All right. Do I have rights? I have rights. Awesome. All right. Can folks see this? I'm assuming the answer is yes. Can you see my
I can
my
see
Yes.
it, Michael.
slides?
Yes,
Okay,
yes,
great.
yes.
All right. Thanks for having me. Yeah, so as Christina said, I'm Michael. Yeah, so my plan for today is to talk a little bit about alert brokering. The talk was originally designed for a time domain conference that I was at a few weeks ago, so it's a bit on the technical side. So feel free to kind of interrupt with questions, and we might blow through um, some slides here as we go. But otherwise, yeah, feel free to just sort of raise your hand or shout out as you have ideas and thoughts. All right, so here's how I think about the optical transient sky, as many of you likely do. So everything that we're concerned with here are light curves. You know, on the y-axis here, we have some measure of luminosity, whether flux or magnitude, and on the x-axis, we have time. And broadly speaking, in our world, we're generally interested in things that uh, explode in some fashion, rise and fall, right? And um, the way that we think about most things in our kind of zoo of transients is to characterize them with a couple of features. One is, what is their peak luminosity, right? How bright do they get? Um, and what is and there's a variety of ways to characterize this, but what is their characteristic time scale? What is the time scale over which they evolve, right? And so this is kind of the two numbers if you were to break down any kind of time domain transient. What do you want to know about a light curve in order to, let's say, classify it, right? And the reason this is useful is because the way that we break down many transients is kind of along these lines, right? So here on the y-axis again, we have peak absolute magnitude, and then on the x-axis we have characteristic time scale. And broadly speaking, we have afterglows on the top left-hand side here. These are things that folks in Kilonova-Catcher have been looking at for a long time. We have FBOTs, which we're going to talk a little bit about here just for a couple of slides. Superluminous supernovae, kind of normal supernovae over here, characteristic timescales of, many, many weeks to months, and on downwards. And so again, the reason that this is nice is because it allows you to kind of point at a part of the parameter space. In this case, for example, kilonovae, most models say they peak absolute magnitudes -15, -16, and they fade on the course of, maybe half a night to a night or so. And you can automatically think about, well, what should it take to identify them? What are the sort of observational timescales? How far away can I see them, right? Just turning absolute magnitude into apparent magnitude, and you have some detector sensitivity, and you can immediately identify that. So, this is you often see plots like this just to say, where does my particular transient of interest fall? And of course, within Kilonova-Catcher and more broadly within Grandma, we're often interested in things that kind of live in this, over here, right? Kind of the hour to day time scale, which requires really rapid follow-up. And generally high energy transients, right? Because the folks in our group are doing things like compact object mergers or, core collapse, whatever. So, and the and again, the reason that we're excited about doing this is because these so-called high energy transients, these really bright objects, they correspond to kind of the coolest stuff, right? Whether these fast blue optical transients, as I said, we'll talk about in a second, tidal disruption events, which I also have a slide on. X-ray transients, the community has started to do a lot of Einstein probe and SFOAM follow-up. And broadly speaking, these correspond to some of the coolest kind of areas of astrophysics, whether you're doing compact objects, neutron stars, or black holes, jet formation, which is always, crosses all sorts of astrophysics. And more broadly speaking, how do our various transient classes connect, right? So, we have examples of core collapse, core collapse of a massive star where you both get a gamma ray burst afterglow plus a supernova, for example. So clearly, these F-bots, folks have posited that there may be, related to tidal disruption events of some kind. And so many of these various source classes connect. And again, we're about discovering more of these. Yeah, so I think I'll just blow through here. I mean, these are a handful of fast transient classes that I've become, or I think are kind of some of the future here, these tidal disruption events, which I have a slide on here, right? So the idea of these tidal disruption events is where I have some supermassive or intermediate mass black hole, and I get tidal disruption of some, stellar object by this black hole. And it's only been over the last kind of the ZTF scale, last, 5-7 years or so, where we've really started to discover a lot of these. And what was really neat is back in 2022 with ZTF, the pipeline that Igor Andreoni and I wrote discovered one of the first jetted versions where actually we could see this very high luminosity X-ray and radio counterpart to this fast transient that corresponded to the formation of a jet, after the tidal disruption of the star. And this was surprising. Well, it had only been seen. I think I have a slide here. Yeah, maybe once before. So, for example, Swift back in 2010 or 11 or so, Josh Bloom at Berkeley published a paper where they saw a bright X-ray transient that they posited was one of these jetted TDEs. And this was the first time we ever found one of these in the optical. And we found it as a fast transient that originally we thought might be a kilonova because it was a fast transient thing. But I think this is just a nice example of, when you go to look at these, high luminosity, short characteristic timescale, that kind of part of the parameter space, you find some cool stuff. And, jetted TDs are one of them. I've also mentioned these fast blue optical transients. So this is something folks like Anna Ho and Dan Purley and others have really gotten into, but they are what they sound like. They're and folks have known about these for a bit longer, even going back to Pan-STARRS, kind of as that survey got going. They identified these, again, relatively luminous, fast rising, fast decaying, relatively blue, i.e. hot transients. That folks still really don't know what they are. But again, they live in this relatively short characteristic timescale, high luminosity part of the parameter space, much more luminous and generally shorter timescale than for sure most typical supernovae. And what makes them super cool is that it's hard. Again, folks don't really know what they are. So, for example, they are too bright to be simply some kind of stellar eruption. For sure, something with this kind of luminosity, it needs to be, you exploded a star, collapsed a star, something like this. They're too fast to be radioactively powered, right? So they're not just some kind of play on supernovae, for example. They're more complicated than that. Um, but on the other hand, they're not some kind of shock breakout. So we often do see kind of um, this relatively fast order, like day or two time scale, kind of fast precursor emission to like a core collapse supernova or something. These 2B supernovae. Folks have all sorts of thoughts on what they might be, maybe some kind of special type of TBE, maybe some weird interaction with the circumstellar medium. But again, these are relatively new. We've only known about them for the last decade. And again, we've only started to really detect them regularly with ZTF. And both for jetted TDEs and FBOTs, and of course, let's say the more normal, fast transients, GRB afterglows, or rare stuff like kilonovae, now that Rubin's turning on, we're really excited to go, do some physics with these as we find many of them. And so this is kind of the optical alert streams that are out there, at least currently. So within Kilonova-Catcher, we often are connected to ZTF, or the Zwicky Transient Facility, which is a 50 square degree imager on the Palomar 1.2 meter. And for scale here, we get something like 300,000 quote unquote alerts per night. An alert is any 5 sigma change in anywhere in the image, and whether it's a known star, known galaxy or not, you get the production of this alert. And there's this huge step up, what I expect to be maybe even 2 orders of magnitude as we move to Rubin. And the alerts, and so Rubin's, that's 8-meter class telescope that we've heard from Christina and others about in the past. And the expected rate per night is 10 to 20 million of these alerts. And so it's really it's a new data processing problem for the community to be able to handle. A survey that you may not have heard of is Argus Array, which is being led out of University of North Carolina amongst other partners. That's funded. It's an array of small aperture telescopes, but a huge array. It's going to image basically the entire visible sky from wherever it sits. It's still to be decided where this thing's going to live, but the expectation is that it will be taking images kind of at the Hertz scale. It's going to, so every second or so, it's going to be taking an image of like the entire visible sky. And so as you can imagine, while the overall alert equivalent in, let's say, a 30-second image is kind of similar scale to Rubin, as you go down to really, really short timescales, the data rates available become just astronomical, to use an appropriate word here. And so the point I'm making with this slide is that there's an incredible opportunity for data science and sort of data processing as we enter this era. And of course, that's supplemented by these multi-messenger facilities, again, some of which we work with, Einstein probes, FOAM, Ultrasat, which is a UV survey that's going to fly, UVEX, which is another UV survey, or other wavelengths, right? SKA, DSA 2000, which will have something like 5 billion sources, right? So and Ideally, you're, for example, cross-matching in real time against, these X-ray, gamma ray facilities or radio surveys. And so, again, these are data science problems that need to be solved in astronomy. And so the way the community, and this is the way I think of it at least, kind of works, is that you have these surveys, whether you're ZTF or Rubin or Argus or LS4, which is kind of like ZTF in the South. It's a survey led out of Northwestern and Berkeley National Lab. And they're producing alert streams that go to these so-called brokers, and that's what we're going to be talking about today, is these brokering systems. There's a bunch of them out there. I'll be talking about the one that we're building to work with, for example, that'll feed Grandma and Kilonova-Catcher as Rubin turns on. And then you have all these multi-messenger instruments, whether you're doing gravitational waves or neutrinos or gamma rays or whatever. And many of you have probably seen or even interacted with these multi-messenger brokers, things like GCN or SIMA, where these surveys are feeding alerts to these multi-messenger brokering systems. And these optical alert brokers and these multi-messenger brokers tend to meet in marshals, which then typically will then disseminate like alerts for follow-up to Grandma or Kilonova-Catcher. And Rubin itself is starting to maintain pages trying to, let's say, herd the cats here to explain, what the different brokers are, what they do, and so on. And so you can get more information there. Now, what's a broker? So first, the way you have to think about this is that you have these large-scale sets of alerts, whether from ZTF or Rubin, and you can think of it as this big fire hose producing, a bunch of water, and you only care about this little snippet of that fire hose of data that's coming out. And again, the scale here is, 20 million alerts per night in this big blue box. But the things that you, as an astronomer who cares about, let's say, gamma ray bursts or something, you only care about a small fraction of these, right? However, you're not the only astronomer in the world. There's, 10, 15 folks on this call. There are many different science cases that one will use with Rubin, and they also have their subsets of alerts that they could possibly care about, and so they're in here too. And so beyond just being kind of this big data problem, for us, there's also a latency problem, right? We're interested in rare stuff that you need to get a spectrum of. We're interested in young stuff, whether you're doing, let's say, you're looking for, lines in some young supernova, right? Emission lines in some young supernova or something. Typically for compact objects, our stuff's fast evolving. So you got to do this stuff in real time is the point, right? So you got to keep up with this with alert stream. And so everything that we've been building and again have been gaining experience with is ETF, which again you've been using. Now the setup is very similar for Rubin, but just to sort of walk through how this works. So I'm ZTF or I'm Rubin. I'm taking images. Those data in the ZTF case go to IPAC, which is on Caltech's campus. For Rubin, the processing is led out of, it's a joint effort between UW and University of Washington and Princeton. They produce alerts, and then something in principle happens, and then you get candidates where the subset of things that you care about, and you need to visualize them somewhere and classify them and onto the community. So there's two big steps here. The first is this brokering or this creation of filters, and so. What do these alerts look like? Typically, they're giving some image data. So science is like the new data taken last night. The reference is stacks of historical data. The subtractions is the difference between the two, plus some kind of cross matches. And then you build filters by, if I'm interested in supernovae, I'll be looking for something that has a host galaxy and maybe above some brightness and maybe with some cut on the age or something. And so I can build filters out of contents of these alerts to identify the things I care about. And so these alerts flow to brokers, which we'll get to in a second. And then once you've identified things that you care about, that pass some filter, it goes on to marshals. Some of you have at least seen or maybe even used Sky Portal in this case, but we're not going to focus on that here. But the idea here is that Sky Portal is one of our interfaces for being able to scan alert streams and then figure out what kind of stuff we want to follow up. But again, we're talking about brokers here today. And for Boom, we've been we're very focused on brokering, and in particular, how we fit within this broader ecosystem of software, both interactions with the alert streams as well with the marshals. And what we cared about is flexibility. For example, we need to be able to accommodate many science cases, not just compact objects, but if you're supernova or TDE, whatever person, we need to be able to support that. Supporting multiple instruments, in particular, we're planning to do joint searches with ZTF and Rubin and do that for the community. And as far as I know, we're the only broker who's going to do that. It needs to be performant, i.e., because we're interested in real time, so we can't have latencies. We can't have, Rubin taking images, producing alerts, and their alerts come out within something like 60 seconds. And then for you to wait hours upon hours to get these filtered alerts, there'd be no point for Rubin to be doing what it's doing if that was true. We need to be persistent. So while the real-time searches are important, there are many science cases where you want to look back in the archive. Even, for example, if I get like a neutrino or binary black hole alert or something, there are cases where I'd want to be able to look back in time to be able to do cross matches. So the rest may seem obvious, reliable, and simple, but again, our experience with building the stuff for ZTF is that since there are other broker choices, user experience is important, and so that's going to be key. And then finally, making it modular is also important. We need flexibility to be able to build out the technology. So what do we have now? We have the system we call Kowalski. It was written in Python. I would say overall is very successful. It drove a lot of, for example, the cross matches we were doing with gravitational-wave and optical searches. It was able to do all of that. It helped with some of the gram and KNC stuff over time. But the reality was, partially because of Python and partially just because of its base infrastructure, it was never going to survive into the Rubin era, right? So this order of magnitude increase where ZTF at times would produce 1 million alerts per night and Kowalski would fall over, right? So if we were falling over at 1 million alerts per night, we're not making it to 10 million. So there you go. We also knew that we needed cross-matching to be a key frontline feature because we are interested in simultaneously doing ZTF and Rubin or LS4 and Rubin. And so the ability to cross-match surveys in a scalable way is critical. And finally, filter building. The experience from ZTF, so we use this database called Mongo, and the reality was even my graduate students struggled to write Mongo queries. And so I'll show us a snapshot of the front end filter building interface we're making such that astronomers can build their own filters and won't destroy the system. So this is what Boom is. So Boom is our replacement for Kowalski. It's built in Rust, which I would say is one of the main sort of keys to its success. Rust is it's a little like the new C. right? Where you're taking care of your own, like, garbage collection and that kind of thing. And it enabled two things. One, it's not an interpreted language, it's a compiled language, so it's faster, but it also just scales better. Python never scaled well, and we found Rust scales much, much better. And so I think the one, just simply moving to a compiled language, as well as the ability to actually make use of many, many CPUs. So here at Minnesota, we've rented a node with 128 CPUs, and we think we can actually make use of them, which, for example, if we were just to put Kowalski on there, it just, the scaling was no good. And so this is the team. It's joint between Caltech, Minnesota, and Berkeley, which is the same for what we did with Kowalski and SkyPortal. So it's kind of some of the same folks at least. So as I mentioned, we'll do multiple surveys. So we'll have ZTF and Rubin alerts, flowing out to Grandma and KNC, which is great. We have some of our own ML classification code that we built out of here at Minnesota. That'll be part of this. As I said, it's written in Rust, and again, we'll show the little filter interface in a little bit. We won't talk too much about architecture stuff. If folks are really interested in this, I'm happy to talk about that. Some nomenclature stuff. So there are only 7 approved brokers to get Rubin data. And it's mostly a cost thing. It's actually very expensive to host a Kafka topic. And so there's relatively limited teams that are approved to actually access Rubin or ZTF alerts. Babamol is our name for our Rubin implementation of Boom. So Boom is the Rust code that one built, and Babamol is the one that's doing LSSD filtering. So if you're ever sort of listening to talks out in the community and people are talking about Ample and Fink and Babamol is the one that we're running. And again, it's just kind of nomenclature stuff. And so again, it's the Babamol stream that folks in Grandma and KNC will be able to listen to, and will be, yeah. Okay, so the kind of stuff that I'm excited about that this enables, one, within ZTF, we've done a lot of work to make, I'll call it automated discovery possible, whether that's enabling, transient follow-up through, so BTSBot is this little machine learning classifier that just asked a question for a single alert packet: is this object real and likely to get above 18th magnitude, so I can get a spectrum of it? And it's been running autonomously for more than a year now. A lot of our cross matches for gravitational-wave and neutrino alerts, like the ZTF triggering, all of that, much of that at least, is automated. And again, it's this automation that we're excited about, because so much of what we need to do in real time is in real time. It was never going to scale well if we were always relying on graduate students to get up in the middle of the night to do it. We have a couple papers now on this apple cider. So apple cider, again, is this machine learning classifier we've built. There's a few papers on the archive I can point folks to. It might be maybe a topic for a future KNC meeting. The other point to make is that a lot of brokers have what I'll front ends, and so it's something that we're still building. I think I'll have a little image of what the current front end looks like. So where we're at, so I should say we're not done, right? So we've been building this. We can successfully process ZTF and Rubin. And so that to us was a big, this was a big milestone where we have a system up at Minnesota, up at Caltech, both of which can ingest the ZTF and Rubin alerts, cross-match them, and do some of the machine learning. So I think we're at the point where I can publicly say this is going to work out. It seems to be scaling well. We've been able to use dark energy camera data. So dark energy camera is not a terrible comparison. It's like a 3 square degree camera on the Blanco 4 meter down at CTIO, and we've run some dedicated ZTF DECAM experiments where we've been able to do the cross matching. And in particular, the science case that we're excited about is we have ZTF objects where, for example, we have pre-detections in DECAM, right? So this is not so dissimilar to what we'll have for ZTF and Rubin, where ZTF will have some bright light curve where Rubin will be able to see, for example, the pre-alerts and the post-alerts. Uh, and I have some example here where, yeah, so this is the ZTF only light curve, but here's what you actually get in DECAM when you include it. So this is, and of course we could never see the pre-alerts in ZTF because it just doesn't go faint enough, right? So this is just amongst other things is why we're excited. So what's made this hard? The alert systems, CTF, dark energy camera, Rubin, they all look different. And again, it's because it's different developers doing this stuff, but it's made us a little crazy. There's different schemas, there's different everything. So this is a pain for filter building and everything. We're trying to take care of some of this, but I think some of the pain will be passed down to users because the reality is the fields are just different in the schemas between some of these telescopes. The other thing I mentioned is filter building. Let's see. So Tomas Colino, who's a postbac at Caltech, has been building front end, back end interface that he's integrating into Sky Portal and other places to, for example, be able to take in this case, so this is like the real bogus score, how real is the transient, some kind of set of operators and then some number, and build a filter with it, right? Which does not feel like a big leap forward, but it just hasn't existed yet for whatever reason, and so we're excited about it because it means that you don't need to know Mongo to be able to make scalable queries, right? And so our idea here is that we'll work with astronomers to write some of these queries, perhaps using the filter interface. We'll make them available as filter blocks, where right now this is just like, is this an asteroid type block? And so people can reuse these same blocks. In the past, like in Kowalski, the number of filters which do the same processing, for example, just trying to ensure this is not an asteroid, it's over and over and over again for every filter. And so we're trying to ameliorate that. I mentioned Sky Portal, where we're working on plugins to connect Boom to Sky Portal, whatever Sky Portal instance. We're also we'll have to be thinking about how to, what the right process to connecting to things like Slack or KNC or whatever is. Where the reality is we're not quite there yet, but we know that we need to do this. The other piece that's happening a lot within certain folks in my group now are the stuff that you need to make sure that stuff doesn't break, right? So we have sort of tracing, let's see, do I have an image? I don't have an image of this, but basically, how long is any given piece of processing taking to try to optimize it as best as we can. We do have a benchmarking pipeline to basically ask, if I check in some code, what percentage change in time is this taking? Does this add 5%? Does it take away 5%? Right? All in the name of trying to ensure that everything we do is, make sure it doesn't slow down and, we don't meet our real-time requirements. The other thing that it will have, and Kowalski had this too, was an API where If you had a user account, you could query the database directly. We're just starting on that, right? But the nice thing about this is, again, we don't want our astronomers or folks in KNC or whoever to have to know Rust or Mongo or anything. But we do need to build out an API client in Python, probably at least in Python for folks to use. And we've started to build it and make some docs and that kind of thing. It does, some piece of it exists. Oh yes, here's my little screenshot of what we started for a basic front end for Boom directly. So this is the kind of thing where we'd expect to make it available to the public. Not even if you have a Sky Portal account. Where does Babimo live? We have filters that are running. We are currently trying to get ports opened here at Minnesota and at Caltech where we can expose the Kafka topics to the world. So that's something I would say the biggest growing pains here are, for the last 7 years, we worked within ZTF or Graham or whatever. Everything was behind firewalls. We never had to deal with kind of generic user authentication. Well, that's happening now. So there is some growing pains that we're having trying to make it possible for, a scientist out in the community to be able to access stuff. Finally, I'm sure any given talk I've shown at this point, as with everything we do, it's fully open source. We always welcome folks to work on this. The challenge is this stuff is highly technical, even relative to our usual stuff. Choosing Rust was, a random astronomer can't contribute type of thing. The Josh Bloom, who is sort of PI of Sky Portal, basically cornered me at some point, being like, how could you make this choice? It means that, no astronomers will ever contribute again. I don't have regrets. I think it's worked well, but it does mean the bar is quite high to contribute meaningfully. But it is open source, and folks are welcome to work on it if they want and such. Okay. Anyways, that's what I got. Thanks for listening. Happy to take questions, and yeah, I'm excited. It's Rubin alerts are flowing. I think we're just about ready to help this community ingest them, and I feel good about that. So that's what's up.
All righty. Thank you, Michael. Yes, so I share for everybody else, I share my office with Antoine and Sushant now, who work on Boom. And there is a lot of neutral comments made about the use of Rust and how much they love it.
Hmm. Hmm.
See
Yep.
that compliment, Michael, that's what you paid me for.
Yep, that's right. Yeah.
So we have, do we have any questions in the audience? Eric Browens is asking how many people are working on it currently.
Yeah, so Antoine and Sushant here at Minnesota, Teofil and Tomat Caltech, and whatever you think PIs contribute to this, which is basically nothing. So 4 to 5 people, I'd say, overall. So it's not that many. Yep.
Yes,
Hey, Thierry.
hi, Michael. That's nice to hear you and to see you again. That's nice. So, of course, I have a question for the amateurs. How do you foresee in near future? How do you intend to plug Kilonova-Catcher to this amazing pipeline? And how do you foresee amateur astronomer could help you in this tsunami of alerts?
Yes. So I think there's 2 pathways to getting KNC alerts. So right now, what happens is for example, gravitational wave or whatever alerts go to Grandma's sky portal instance, and then Damian has some scraper that pulls from the Grandma sky portal instance and like puts it in Slack, puts it in the KNC website. That's my nominal pathway. I think the other pathway is a direct read bypassing Sky Portal where, some version of Damian Scraper puts things in Slack, puts things on the KNC website, and we roll that way. I'm hopeful, and I haven't spoken to Damian about any of this. But my current plan is the Sky Portal route, if only because like the software changes are at least trivial within that script to be able to like get, make the Slack stuff line up. But so that's as much thought as I put into this. I think the other, as I said, we're also going to have a dedicated front end, which again does not exist, but I am looking forward to, once that does exist, having people just like try to make accounts and just try to break it, because we're going to need people to try to break it. Because so far it's, it's like the 4 or 5 people working on this as many of you with your engineering backgrounds know, nothing is real until it's in production, and then we'll see how we're doing. But so that's my so to summarize, I'm gonna need you to, as soon as stuff is available, try to break it, because that's great. And then 2, engage with Damian as we try to figure out how to make the data workflow fit within our usual KNC stuff.
Okay.
What is your thoughts on that 5 billion alert stream for one of the radio observatories that you showed at the beginning of the
Yeah,
presentation?
if I was doing DSA 2000. Yeah, I mean, so just for folks understanding, so there's this, and it's funded now, this array of 2,000 radio dishes that Greg Hallinan at Caltech's PI, and anyways, there's other Caltech folks involved. I suspect they have not thought a lot about their filtering needs, just knowing the parties involved. But I mean, maybe they have. But the way those radio instruments usually work is they'll have something like a FPGA or similar that's right there at readout, because they have so much data streaming in where they need triggers to actually have them like save their data, right? Because they can't save everything. And so I think they'll have something like the high energy physics community has, I suspect, which will be so in high energy physics parlance at CERN, they have a level 1 trigger where, so they have data flowing in, they have an FPGA, some machine learning, some basic filter that triggers them to save their data, and then it goes downstream to some like classifier or some downstream analysis. I suspect that that's something similar will have to happen for DSA 2000. But yeah, I'm glad I'm not needing to deal with that, because that's a whole other scale from the Rubin problem. Rubin already feels hard, and yeah, the radio folks are going to have all sorts of trouble. Yep.
How does that and then how does that compare to like what Lisa would be getting? Like, I know it's a whole different type of problem because it's not light, it's gravitational waves, but what is Lisa looking at compared to like
Well,
LIGO?
so Lisa, because it's low frequency, is not nearly as hard, right? So because they're not taking, they don't have like even a 16 kilohertz stream. So Lisa has a challenge, which is, of the data that's there, they have all these gravitational wave sources sitting on top of one another. I think there may be some interesting kind of low latency problems for like early warning type things, if you're like early, because they're going to be able to see some, binary black holes long before they merge type thing. So there's probably some interesting processing there, but yeah, Lisa kind of faces a different challenge.
Do you have any other questions?
Thanks, folks, for having me. I really appreciate it. Yeah, so feel free to reach out if you want to get involved, but you'll be hearing more about this in the coming months. This is happening, and it's happening soon. Yep.
I hear about it all the time. The updates for this will be, you can reach out to Michael, you can reach out to me. But I think this talk was really good timing, given all the discussions we've had, and hopefully the new funding coming from France and hopefully from NASA in the coming months for KNC to start implementing these things and give you guys some more access and control to the tools that are necessary for the next era of multi-messenger astronomy. All right, thank you so much, Michael. And thank you everybody for coming. Have a great day, all.
Thank you. Have a good day.
Thanks a lot, Michael.
Bye.
Thanks, Christina.
Of course.
Thank you.